Good morning to everyone. Good morning. Okay. So shall we start with the class? So before going to the today's concept, what we had discussed in the last class, we have discussed about groups and which is also called as groups or families. Groups can also be called as groups or families. That's what we have discussed about the elements present in the groups. Right? So what are the special features of these groups or families? So I am talking about, in your textbook it will be related to 3.3 only. It is related to 3.3 groups or families. So where even I can include 3.5. That's what yesterday we have discussed. 3.4 we have not discussed yet. Okay? So that's where we have groups or families. Now in the periodic table, how many groups are there? Total 18 groups are there. Right? So total 18 groups in the periodic table. So groups are nothing but vertical columns. Groups are nothing but vertical columns in the modern periodic table. So don't write MPT. I have used that short form. Don't use that one. So modern periodic table. That's where we have the vertical columns in the modern periodic table. So how many groups are there? 18 groups are there. So that means it will start from 1 to 18. So group 1 to until 18 it will be there. Fine, all of you will agree? So that's where we have the groups. Now, what are the features of the elements present in the groups? They will be having similar outer electronic configuration. Similar outer electronic configuration. Right? So this is the feature of elements present in a particular group. For example, if I take the example, those elements which are present in group 1 will have outer electronic configuration as NS1, alkali metals. So those present in group 2 will be having outer electronic configuration as NS2, alkaline earth metals. So if I take group 13, that is boron family, so it will be having NS2, NP1. All the elements will have NS2, NP1. So like that it will goes on. And finally we will be having group 18, which will be having NS2, NP6. So that's where we have the features of the elements present in a particular group. So what are groups? They are nothing but vertical columns in the periodic table. So total 18 groups are there. What is the similar features of those elements present in a group? They will be having similar outer electronic configuration. This is where I have given the example. So where group 1 will be having NS1, group 2 will be having NS2, like that it will goes on. So all the elements present in group 1 will have similar outer electronic configuration. Only n value will be changing, right? So 1s1, 2s1, 3s1, 4s1, like that it will be changing. So that's what yesterday we have seen. And due to that, due to the similarity in the outer electronic configuration, what will happen? What is the consequence? What is the consequence of having similar outer electronic configuration? What will be the consequence of this? Anyone? Any one of you? What will be the consequence of these things? Having similar outer electronic configuration. So due to that, they will have similar properties. All of you are correct. Very good. So due to that, they will be having similar properties. That's why they are using the term family. Right? So they will be having similar properties. All of you have understood? That's what we can understand from the groups in a periodic table. Okay? Now we will move to the next one. Next one is what we have discussed in the last classes, that is about the periods. That is about the periods, right? Now we have discussed about groups. Now we will talk about the features of the periods. Now when I am talking about periods, right? So that is nothing but a horizontal row in the modern periodic table. Horizontal rows in the modern periodic table. Don't use MPT. To save the time I am writing, but you don't use that one in exam and all. So that's why we have the horizontal rows in the modern periodic table. They are nothing but periods. Now in the name itself it is there, periodic table. So why it is called as a periodic? Somewhere it is related, periodic table. So that's where if you go with Newland's theory, first element, and when you go like this and once again you come back, whatever element will come over here, they will be having similar properties. So that's where period indicates. After some after some elements, there will be coming entry of another element which will be having similar property as that of which we are interested. So that's why they are called as periods. That's why they are called as periods. Now, when I am talking about the periods, there are total how many periods? There are total 7 periods in the periodic table. There are total 7 periods in the periodic table. Yes, but only thing here is elements present in the period. Elements of a particular period will not be having particular period, will not be having similar properties, similar outer electronic configuration, will not be having similar outer electronic configuration, and therefore differs in their properties, right? So that's what we can conclude. So those elements present in a particular period will not be having similar outer electronic configuration, and therefore naturally they don't have similarity in their properties also. That's what we can see here, right? Now next statement is, whenever we are moving from period 1 to period 2, whenever we are moving from, example is from one period 1 to period 2. So that means we are moving to the next energy level. That indicates that we are moving to the next energy level. That's what we have observed. We are moving to the next energy level, right? When we are moving from one period to next period, right? So that's where we have the observation. Now, in the same period, what will happen in the same period? If you are moving from left to right, in the same period. In the same period, what is happening? We are in the same energy level. We will be in the same energy level. There is no increase in the energy level when we are moving from left to right along the period. Right? So that's what we can observe. But when we are moving from one period to another period, then there will be difference in the energy level. So period 1 indicates energy level 1, right? So that's where n value will be equal to 1. If period 2, n value is equal to 2. Period 3, n value is equal to 3. So like that it will goes on. What is n? So we will consider n as outer energy level. We will consider that one as outer energy level or valence shell in this case. Generally, n is nothing but principal quantum number which talks about energy level. But here, n will be considering valence shell or outer energy level. All of you have understood? So that's what we can observe with related to the periods. That's what we have discussed in the last class. Then we have discussed about S and P block elements. We have discussed about S and P block elements. Okay? So now, when I am talking about S and P block element, what are the features of S block elements? What are the features of S block elements? Right? Then we have discussed about S and P block elements. Right? In the last class even we have discussed this one. So when it comes to S block, which are those elements or groups which belongs to S block? Anyone? Which are those groups which belongs to S block? So which are those groups? Those groups are 1 and 2, right? So group 1 and group 2, right? Absolutely correct. We have the S block where we have group 1 and 2. Group 1 is alkali metal, group 2 is alkaline earth metals. So single positive charge, double positive charge. So therefore NaCl, MgCl2, magnesium chloride. That's what we have seen. So therefore I can tell NS1 and NS2, right, as the outer electronic configuration. Fine. So that's where we have the S block element. Naturally they are metals. They are metals. Now when it comes to P block, it will start from group 13 to group 18. When I am talking about P block, it starts from group 13 to group 18. Yes, S block elements are metals. Absolutely correct. Right? Then comes the P block. Right? Yes, group 13 to group 18. Right? So first will be a boron family, then carbon family, nitrogen family, oxygen family, fluorine family, and then comes the helium. Okay? Then comes the inert gas. Helium, neon, like that it will go on. Don't think they are in the same period. No, I am just writing the group, first element of that respective group. I am not talking about they are in the same period because helium will be in the first period. Okay? So helium family. So now these are the elements which belongs to period number 2. They belongs to period number 2. But this belongs to period number 1. Okay? So that's where we have the boron family, carbon family, nitrogen family, oxygen family, halogens, then inert gas, which are also called as zeroth group. Inert gas elements are also called as, group 18 is also called as zeroth group element. Fine? Now, why they are called as inert gas? Because they are very less reactive due to the completely filled electronic configuration. Stable electronic configuration. Now, when it comes to halogens, they are very reactive. They are very good acceptors of electron. One electron they will accept very fast to attain the electronic configuration of the inert gas. Now then comes the rest of the elements which are also quite reactive in nature. Fine, all of you have understood. So that's where we have the group 13 to 18 which are nothing but p block elements. What is the general electronic configuration? General electronic configuration will be NS2 to NP1 to 6. That will be the general electronic configuration for p block. Now, S and P block, generally they can be considered as representative elements. Representative elements or main group elements. Anything is fine. Or main group elements. Okay? So, why they are called as representative elements or main group elements? Because of their reactiveness. Alkali or alkaline earth metals, they are reactive. P block elements, they are reactive, especially when you move away from nitrogen, then they will become reactive, especially that halogens, they are reactive. And when it comes to P block, we have metals, non-metals, metalloids, right? Like silicon, germanium, polonium, astatine, they are all examples for metalloids. Okay? So that's where we have the speciality of the P block. Yes, absolutely correct. They are having all the types of element in P block. I am not talking about S block. S block, they are metals, no doubt. So due to their reactiveness, and especially when it comes to P block, we have all the types of elements. Therefore, they are called as representative elements or main group elements. And there is a uniformity in their properties. There is a uniformity. That's why they are called as main group or representative elements. So these are the things which we have discussed, and you can expect 1 mark question from this part. All of you have understood? Fine. So we will move to the next one. That is D block elements. We will move to the D block elements. Anyway, I am not going to discuss this one in detail. Okay? Because this is not there in your first PU. It's there in your second PU. Separate topic as D and F block elements. But I will give a brief view about the D block elements. Now, to understand this, once again I am going to write a flow diagram. Okay, so 3P, 3D, 4S, 4P, 4D, 4F, then 5S, 5P, 5D, 5F, like that it will goes on. Then I have filling of electron. So this is how electrons will be occupying respective energies, energy level. So that's where I have this 6S, 6P, 6D, 6F. Okay. So like that it will be filling it up. Fine. Now to write the electronic configuration, we will write the inert gas. Helium, neon, argon, krypton, xenon, radon. So this is 2, this should be 10, this should be 18, this should be 36, then it should be 54, then it should be 86. Right? So that's where we have the atomic numbers of inert gas. If you have this information, we can write the electronic configuration. Now, can any one of you write the electronic configuration for zinc? Zinc atomic number is 30. Zinc atomic number is 30. Okay? You can try it out. Electronic configuration for zinc. Now if you observe the inert gas, we can take the help of argon where it is 80. But krypton is 36. We cannot go with 36. 80. Now 30 minus 80. Leftover will be, it will be 12, right? So leftover will be 12. So we have to show the electronic configuration for 12 electrons. Now when I am writing argon, I have done 18, period 1, period 2, period 3. So that means I have done it up to 3p6. Period number 3 I have done, right? So I have to go for 4s, 3d, 4p. I should take the help of 4s, 3d, 4p. Then I will write it. I will first go with the lower number, that is 3d. Then I will go with the 4s. Then I will enter the 4p. It's up to you. No need to worry. You can write 4s, 3d, 4p. That is also fine. No need to worry. Fine? Okay, 4s to 3d, 10. Okay, 4p up to 4p it will not go. Okay, fine. So because we will be requiring 12. Yes, 4p is not required. Okay. So we can write it as 3d, 10, 4s2. Right? So that is one of the element in the D block. That is one of the element in the D block. Can you write the electronic configuration for iron? 26. Iron 26. Atomic number for iron is 26. Once again, same period it belongs to. So we should take the help of argon. Okay. Now 18. So 26 minus 18. Right? 26 minus 18. Naturally it will be 8. Leftover will be 8. That means here only somewhere I should write. I can write it as 3d, 4s. Now fill the number. You can fill the number. Anything else is there which I can write? Okay, fine. Absolutely correct. It will be 3d6, 4s2. Right? 3d6, 4s2. Now, if iron will lose electron, then it can go for 3d5, 4s2. Another one electron, then it will become 3d5, 4s0. That's where we have the iron, which can be in multiple oxidation state. Especially, it will be present as Fe plus 2, Fe plus 3. And Fe plus 3 is quite stable because there it will be having 3d5. Okay, anyway, we will not discuss that one. So that's where we have written zinc and iron. Now write it for chromium. Now write it for chromium. Atomic number is 24. Same period I am talking about, but they are all example for DBlock element. Chromium 24. Now once again we should take the help of argon. Once again we should take the help of argon. Write the electronic configuration. That means 24 minus 80. Right? So now that's where we will be having 6. Naturally, here it is 8, here it should be 6. Now how to write? Any one of you have written? Okay, 3d4, 4s2. Okay, that's where I want you to understand. Here, when it comes to chromium, it will go with the 3d5. It will go with the 3d5. Then 4s1. It will go with 3d5 and 4s1. What is the reason? The reason here is it wants to have the stable electronic configuration. That means half-filled electronic configuration. Half-filled electronic configuration. So therefore, it is going for 3d5, 4s1. Otherwise, according to above principle, yes, it should have been 4s2 completely filled. Then whatever left over is there, it should go to 3D, where it will become 3D4. 4s2 3D4 would have been based on above principle. But that is not universal. When it comes to especially D block, it is not universal. Above principle everywhere it will not applicable. Some of the elements they will go for stability. Half filled electronic configuration is stable. So that's why chromium will do like this. But once again, this is also not universal. Whatever I have written, this is also not universal. Platinum, another example, platinum which is a stable element, right? Like gold and silver. But platinum will have the different format. It will go for 3D9 4S1. 3D9, not 3D9, sorry. It will be having D9 and S1. If I would have been there, I should have made it as D10. I should have made it as D10 because it belongs to 6th period. Okay, now? So I would have made it as D10. But instead of that, it will keep it as D9 only. And another one as S1. It will not make it empty subshell. It will keep half it for S1. I am talking about platinum. Okay. So what I mean to tell you is there is a variation. When it comes to D block, there is a variation. Right. So everywhere, everything will not be universal. Fine. All of you have understood? So that's where we have the zinc, iron and chromium. Yes, even copper also same thing is applicable. Yes, same period it belongs to. All of you have understood? That's where we have the speciality of the D block. And someone yesterday they were telling penultimate shell will be incompletely filled. But I told it's not universal. Because even outermost shell can be incompletely filled. Fine? So what I mean to tell is, but in general we can tell that, most of the element, 90% of the element in a D block will have the incompletely filled D in penultimate shell. Penultimate means which is before to the outermost shell. Okay, just before to outermost shell. So they are called as penultimate shell. Yes. In the general we can tell that they will be having incompletely filled. They will be having incompletely filled penultimate shell. But they are not, it's not universal also. It's not applicable for all the D block elements. Fine? But we can tell most of the element which belongs to D block, they will be having incompletely filled penultimate shell. Right? So that's what we can observe. Outermost energy level is 4, valence shell. Penultimate is 3, incompletely filled. Right? Same logic is applicable, but here even outermost shell is also incompletely filled. Fine? But when it comes to zinc, all are completely filled. So therefore, please remember, zinc can be an example for pseudo transition elements. Even cadmium, which belongs to the same group. Zinc can be an example for pseudo transition elements. Anyway, these things we are going to discuss in your second PU. Why they are called as pseudo transition elements? Because since they have completely filled electronic configuration, they will not show most of the property shown by the rest of the elements of D block. Whether I am clear? Zinc, cadmium and all which belongs to the same category, they will also will be called as pseudo transition elements. Zinc can be the best example. Okay? Now, pseudo means, okay fine, I will repeat. So zinc is one of the best example for pseudo transition element because they have the completely filled electronic configuration. That D subshell is completely filled. But according to D block, they should be having incompletely filled D subshell. Right? But they have the completely filled D subshell, and due to these completely filled subshells, that means outermost and penultimate shell which are completely filled, they will not show most of the properties shown by D block, rest of the elements of the D block elements. They will not show most of the properties. Whether I am clear? For example, they can show only one oxidation state, that is +2. Zinc can have only zinc +2. They cannot have zinc +1. They cannot have zinc +3. Only one, zinc +2. Like alkaline earth metal, which will have +2, even zinc can have only +2. But rest of the element, they can show multiple oxidation state. For example, we have copper, copper +2. So this is called as cuprous. This is called as cupric. Same way, iron +2 +3. This is called as ferrous. This is called as ferric, right? So whenever OUS is ending, lower oxidation state. Whenever IC is there, higher oxidation state. But don't think that IC, ferric, cupric, applicable everywhere, this +2 only. No, when it comes to iron, +3 is called as ferric, IC. OUS, ferrous, is lower oxidation state, that is +2. So depending on the element, but higher oxidation state of respective element will be ending with IC. Lower oxidation state of respective element will be ending up with OUS. Fine? So that's where we have the multiple oxidation state. Right? But there are some elements which can show single oxidation state. But most of the D block element, they can show multiple oxidation state. That is the speciality of the D block. That's where they differ from alkali or alkaline earth metals. They are constant. Alkali metal always +1. Alkaline earth metals always +2. Right? But when it comes to D block element, they will have the multiple oxidation state. That's how they differs. Although D block elements, which are called as transition elements, transition metals, they can be called as transition metals, but still they differ from the alkali or alkaline earth metals with respect to their oxidation state. Here they can show the multiple oxidation state, but when it comes to alkali or alkaline earth metals, they can have the specific oxidation state. Whether I am clear? All of you have understood? Fine. And another difference between S block metals and the D block metals here is, when it comes to D block element, penultimate shell will be, most of them will be incompletely filled. But when it comes to alkali or alkaline earth metals, this is not the scenario. Penultimate shell will be completely filled, outermost shell will be incompletely filled. Fine? All of you have understood? Even if I take outermost S subshell only, then even that is completely filled when it comes to alkali or alkaline earth metals. But that is not the scenario in D block. Any doubts? All of you have understood? Fine? So when it comes to D block, always it starts from period number 4. I am talking about period 4 elements only. Whatever I have written, they are all belongs to the same period, not group. They belongs to the same period. Right? That means D block elements start from period number 4. Right? So that's where we have the 3D, which is getting filled. When I am moving to the energy level 4, 3D is getting filled. So in that case, what should be the general outer electronic configuration? What can be the general outer, one mark question can be asked. So what can be the general outer electronic configuration? So we can tell, or we can write that n-1d, right? n-1d, it can be 1 to 10. n-1d, 1 to 10. Then ns, 1 to 2. 1 to 2 or 0 to 2, anything is fine. We can even write it as 0 to 2. But 0 is not there, but still 0 to 2 or 1 to 2, anything is fine. So n minus 1, d 1 to 10, ns 0 to 2 or 1 to 2. So that's where we have the general outer electronic configuration for D-block elements, which are called as transition elements. All of you have understood? Any doubts? So that's why I have written chromium, to make you sure that why ns 1 to 2 or 0 to 2. Why the hell 0 to 2 we have to require for ns also? Because in D block, D subshell will be getting filled up, right? S subshell should have been completely filled. But why we have to write like that? To make you understand, I have written for chromium, where we can see it is 4s1. Fine? All of you have understood? So that's where we have the D block elements. Okay? So that's where we have the D block elements. So now, to brief it out, now today's class is not over. Since I have written many things on the board, you might be getting confused. So to brief it out, when it comes to D block elements, first and very important point what we can mention here is they are called as transition metals. And in the name itself it is that they are metals. They are metals. I will come back to metals, non-metals and all afterwards. But for time being, remember that D block elements are called as transition metals. Why we require transition word? That's what yesterday I told. Transition because they are present between the S and P block elements. So they are present between the S and P block element, where we are moving from metals to non-metals, because in P block maximum 90% will be non-metals. So we are moving from metals to non-metals. That's why they are called as transition metals. They are present in between the metals and non-metals. Fine? So there is a transition which is happening. There is a transition which is happening. There is a change, slow change which is happening from metallic character to non-metallic character. So therefore they are called as transition elements. And most of them, all of them, they are metals only. That is first thing. Right? Now, another important property here is most of them have incompletely filled. Most of them have incompletely filled penultimate shell. Most of them, they have incompletely filled penultimate shell. That is another important point. Most of them have incompletely filled penultimate shell. Fine? That is another important point. Right? That's what we have observed. D subshell, which is 3D, it was incompletely filled, and 4S in many of the elements it was completely filled. But I have written most, I have not written all of them. Don't write all of them. You should write it as most of them have incompletely filled penultimate shell. Fine? So now, the most of them can show, most of them have or ability to show multiple oxidation state. Multiple oxidation states. That is the thing, very important part. That is applicable for D block elements. Right? But naturally, if any one of them you ask, define D block element, then you can tell that, I will extend this one only, you can tell that if I want to define the D block element,